Do I want you to fear or love vector calculus? Easy, both. I want you to be afraid of how much you love it. So I guess we need to learn about the cross product today. The cross product is just a way of combining vectors in a multiplication where you multiply two vectors together and you get a vector out of this. So this is like, it's not the dot product. So it may feel similar to the dot product, but a lot of people will get this sort of confused, one versus the other. This has a different set of properties and it has a different set of tools or uses that we're going to use. So the cross product is a way of finding a vector that is mutually orthogonal to two other vectors. Now, uh, when you first look at a problem like this, asking for a vector that is mutually orthogonal to two vectors, at first you might say, well, what in the world are you talking about? So let me try to illustrate this with, well, here we are. I have two vectors, and if I want a vector that is perpendicular to both of these, that's what mutually orthogonal means, is vector that's perpendicular to both of these, it would be one pointing directly at you, because that would be perpendicular to this vector here and this vector. So that's what we're talking about. And on the surface, the first thing that comes to mind when looking for such a vector would be to use the dot product, because we know that the dot product of two orthogonal vectors is 0. And you certainly could do that. But I'm going to skip that. Normally I would do that in class or have you suffer through trying to find these mutually orthogonal vectors. But let's skip that and get right to the cross product, because the cross product is the answer to this question. Okay, my iPad is not showing me all of the equations, so I'm going to have to add to each one of these, but not to fret. So a matrix is just an arrangement of numbers or an array of numbers. Usually it has brackets around it. This one doesn't. And actually none of them do on my PowerPoint on the iPad for some reason. So getting back to this, um, so we're going to be, I need to give you a quick primer on using matrices, because the matrix is the way that we're going to be computing the cross product. So to compute a determinant of a matrix, what you do is, so this is, let me just go back here. We're going to call this matrix A. And then to get the determinant of A, what you do is you multiply the diagonals. First of all, you augment. So I've taken this column and copied it down over here. And then this column, I've copied it down over here. Now, if you want to know why, you're going to have to take linear algebra. I just want to show you how to do this. Now, some of you know how to do this already, so it's not a big deal. But notice I'm just copying those columns over, and then to get the determinant, what we're going to do is we're going to multiply through all of the diagonals of this matrix. So here's what that looks like. And then the key is, notice that, so the determinant of A, what you do is you get these down diagonals. So for example, this down diagonal, and you make all of them positive. So here's another down diagonal here. So notice that's this one, and so on. Make those positive, and then all the up diagonals, we're going to make them negative. So you add together all the down diagonals, subtract off all the up diagonals, and then if I get out of the way, you can see the whole thing. And that will give you the determinant of the matrix. So getting back to the cross product, U crossed with V, the cross product of vector U and vector V, is the determinant of this matrix here. So probably it would be helpful if we had an example of this. So we'll do that, and then we'll switch to the next video for the next thing. So let's go back to this. Find the cross product of these two vectors. So the way you're going to do this is you're going to, oh, and this is the whole business of the orthogonality thing. Anyway, U crossed with V is going to be the determinant of this matrix, where you have I, J, and K in the top row of the matrix, and then you write the numbers for vector u along the second row, and then the numbers from vector v along the third row. So let's go ahead and do this. So we will copy this down here. 1, 1, 1, 1, negative 1, 1. And now remember, we're gonna take these first two columns and you're gonna copy them over here. So basically I just copy the entire column. So I, 1, 1, J, 1, negative 1. So that's step one of finding a determinant. Step two is to work out the diagonals. So we have to find all the diagonals. And so I'll do this down, down, down. And I'm just going to go ahead and multiply this out. I times 1 is just I. J times 1 is just J. K times 1 times negative 1 is negative K. So those are the down diagonals. Now we'll do the same thing with the up diagonals. So let's see, that's this, this, and this. So this up diagonal is 1 times k, which is k. The next one is negative 1 times I, which is negative I. And then 1 times j, which is j. Now what we'll do is we'll combine all this stuff. All of the down diagonals we add together. So I have I plus j plus negative k. And then you subtract off the up diagonals. Minus k minus negative I minus j. Now we'll do whatever algebra we need to collect like terms, and we'll have our final answer. So I have, it looks like 2i. The j's are going to cancel, minus 2k. And I could write this like this, 2, 0, negative 2. And that is the cross product of these two vectors up here. Now in the next video, we'll look at why we would care and what the use of the cross product is. I think that's enough for now, at least to give us a flavor. Ooh, can you see this? There, now you can see it. All right, so we'll pick this up again in the next video.